Hi, welcome to General Relativity in Curved Space, the next lecture in Extraordinary Concepts in Physics, Physics X, being taught at Michigan Tech. So I am Robert Nemiroff, your cosmological coordinator. This is Michigan Tech, as it's been advertised. So this course is being taught it's available on the web through iTunes and through the web on Starship Asterisk under Physics X. You can search for that in Google. You don't really need a lot of math, you just need a lot of curiosity, and we'll be going after the main concepts. So today we'll be going after the main concepts of general relativity. And so let's go right to it. So general relativity, we'll review next slide, is actually a theory of gravity that was created by Albert Einstein. It supplanted Newton's theory of gravity, which had been operating for a long time. Newton's theory of gravity actually is arguably the more important theory of gravity today because it describes almost everything we need to know about the solar system. There's only small oddities that Newton's theory doesn't seem to account for that it's useful to pick up with Einstein's theory. Nevertheless, it's a monumental achievement. It's amazing that such an accurate theory of gravity on large scales can be created. In Einstein's view, there is no real force of gravity. So you're not supposed to speak of force as you are in the Newtonian concept. There is space-time curves. There's different geometry which causes curvature. Most of the time, general relativity is very close to Newtonian gravity. After Einsteinian gravity, the general relativity was formulated and published in 1915. It was tested. First of all, it was created to describe the precession of Mercury, which was known to be an oddity that couldn't be described accurately with the known Newtonian gravity. Actually, that also a key test came with the deflection of starlight in 1919. As about mechanisms, well, curvature is a way of picturing what goes on. There's no real known distance at a force, action at a distance mechanism for gravity. No theory of gravity beyond the mathematical form, as Richard Feynman is partly famous for saying. So Einstein was constantly thinking about gravity, even before he published general relativity. So special relativity was published in 1905, general relativity 10 years later. All along the way, Einstein got it wrong a lot. So don't be mad at yourselves for not coming up with your own theory of gravity so quickly. It took Einstein quite a bit of time to do it. In fact, in 1912, he published a theory that wasn't exactly right. It got the wrong deflection of starlight. And so when they went out to measure the deflection of starlight, they couldn't because it is cloudy. They would have gotten the wrong answer, and Einstein would have been thought of maybe as the person who guessed wrong on gravity. But then Einstein published general relativity, GR, in 1915, which was better than the 1912 theory. And in 1919, they finally had a clear enough field so they could see a total eclipse and see the moon block out the sun so you can see the deflection of the background stars, and it agreed to within some errors with general relativity in 1919. And so that helped catapult Einstein to be a superstar. In the 1920s, he got a Nobel Prize, partly, they said, to make the Nobel Prize more famous. He was that famous. So general relativity today remains our most accurate theory of gravity. Scientists sometimes debate what would have happened if Einstein hadn't existed. Would we still be living with rocks and fire? Well, we weren't living with rocks and fire then, so that's unlikely. Special relativity, people think the general consensus is would have come up. We'd already had Lorentz contractions, a lot of the details. It was a very strange way to think about things, but a lot of scientists and historians believe that special relativity would have come about. General relativity might not have come about. I don't know what theory of gravity we would have today. It certainly would be more sophisticated than Newtonian gravity, but it might have been a while longer before we came up with general relativity, if ever. So thanks to Albert for that. So in general relativity, there's some key things. First, that there are local effects as opposed to global effects. So things that are very near to you are considered local. And in that time, space-time is considered relatively flat. So even if you're in a curved space-time, the area right around you is flat to you. So many times when things like clocks run slower in general relativity, no matter what happens, when you look at your wristwatch will always appear to be going the same speed to you. It's people who are far away. It's their wristwatches, or their clocks that might appear different. And the same is true in special relativity. So the idea is that space near mass curves time near mass slows, again, as seen by far away. So that's the way I like to picture general relativity, even though it doesn't get into the space curvature effect. I like to think of it as near mass as time runs slow. And that can conceptually, in my mind, account for things in a way that I can picture things a lot better. Equivalence principle we'll get into this lecture. All things fall together is a simple statement of that. Birkhoff's theorem is important because it allows you not to have to include the whole universe in your calculations. You can ignore symmetric stuff that's outside your sphere. Gravitomagnetism will be touched on briefly. That is trying to undergo more rigorous testing even in today's world. So that's gravitomagnetism is to gravity as the magnetic field is to the electric field. It is an analogy that works. Okay, so space-time is another key concept, so we're big on concepts here. Space-time really is just taking the three spatial dimensions and considering time to be another dimension that only goes in one way. So time is like a fourth spatial dimension. So many times you will see things put on these sheets here, like this. This doesn't make some sense in the sense that why would the Earth push down if it wasn't for gravity itself? So this is a way of picturing curvature. So there's no real gravity pulling down or the whole thing would be strangely circular. Okay, so we'll start off with, we'll continue with one of these concept quizzes that I'm so fond of. So you're in a small elevator. Poof, I can just put you in a small elevator just by suggesting it. Is it possible to tell you are accelerating downward in this elevator without gravity or near a gravitating mass? Can you tell the difference between the two? So you're in an elevator, it's one of those two things, you're told. You're either standing on the bottom of the elevator because there is a big mass below you, could be the Earth, or possibly you're accelerating. The elevator could be accelerating in the other direction. So could you tell the difference? No, yes, or only if the elevator eventually stops. So let's kill those things. And the answer is no. In general relativity, pure linear acceleration is indistinguishable from gravity. This is a statement of the equivalence principle, which we'll get back to. You can't tell the difference. So again, I can put you on a small elevator. This time you're asked whether you are near a gravitating mass like the Earth or if you're in a space station spinning to produce artificial gravity, something like the famous film 2001, A Space Odyssey by Arthur C. Clarke. Can you tell the difference now? No, it's pretty much the same. Yes. Or you can tell the difference only if small elevator is a euphemism for physics hell. And the answer is yes, actually you can tell this space. That's not exactly the same. The artificial gravity created by rotation is inherently different than gravity, although it may feel the same at first. One way to tell is to rapidly spin some object, like a top. So if you spin some object, let's say a top or something, just a ball. So you spin a ball. That's a simple object. And you spin it around this axis here. Then the object will try to maintain its spin axis. Except if you're on a rotating space station, the space station will rotate around you, and so suddenly it will appear, strangely, that the spin axis of the ball is changing as you rotate around. That doesn't happen in regular gravity, so there's a way to do it. So you don't have to look outside the elevator, you don't have to look for distant stars. That's a way of telling. And these little thought experiments are important to people for visualizing what's going on, for people creating them to understand what the key differences are. So here's getting into the equivalence principle some more. There's a famous equivalence principle, first created by Galileo, when Galileo dropped things from a tower, the Leaning Tower of Pisa, and supposedly saw them hit at the same time, although they could not have exactly hit at the same time. But the equivalence principle test was done much better by actually astronauts on the moon. And here's one right now I'm going to play for you for the next 48 seconds.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that? This proves that Mr. Galileo was correct in his findings.
Okay. So it is only when there's a numerical equality between inertial and gravitational mass that the acceleration is independent of the nature of the body, said Einstein. So the weak equivalence principle was tested there that all objects fall the same in gravity. So this was a revelation to me when I was an undergraduate in physics. I kind of heard about it in high school and wrote it down, but really it's kind of strange that very massive things and very light things, they fall the same in a gravitational field. There's no difference. The strong equivalence principle is actually more strong. It says that all experiments appear the same. One aspect of this is G should be the same in the early universe. So this is the guts of general relativity, is all this curvature stuff. So this is a way of describing curvature. This is the time. This is radius out from some central object. This is theta around the object. This is phi. They consider them like spherical coordinates. And ds squared is sort of like a null path where photons fly. It's sort of like the square of the sums of all of those. It gives you the net amount. So for the null geodesic is 0, where photons fly. So there's different kinds of ways to define things in space-time. So sorry about the font going bad there. It's Google Docs for you sometimes. So let's say two events happen in space-time. They're separated in space by delta r. So there's just make things easy and make delta theta 0 and delta phi 0. You can always do that. And they're separated in time by delta t. If one event can affect the other, if c times delta t is greater than delta r, that would be considered a time-like interval. A space-like interval would be if c delta t is less than delta r, then one event cannot affect the other. If c delta t is exactly equal to delta r, then you have a light-like interval, where light from one would exactly affect the other. Important concepts in general relativity. A really cool concept is something called a closed time-like curve, where a curve that comes back to each other, delta r is 0 here, the absolute value of delta t is less than 0, a curve that comes back to the same point at an earlier time or even a later time. In general relativity, that means you can come back to the same point at a later time. Now we can just come back to later, we can do that here, that's not a problem. But general relativity allows that it's time reversed, it doesn't have a time direction. You can come back there at an earlier time. So backwards time travel, traveling to your past, is not forbidden in general relativity by the equations. We need, I guess, some other physics to allow it. Something else has to come in. A chronologically protection conjecture like Hawking made. So this will be discussed, time travel will be discussed in detail in other lectures. So look for that. Okay, moving along. So what about energy conditions in general relativity? Other concepts inherent in the center of general relativity. One is a concept of time symmetry. Actually, M.E. Noether, a famous physicist and mathematician from early in the 20th century, came up with a very powerful theorem, which I believe I alluded to in an earlier lecture, that every time you have some kind of symmetry, you have something conserved. So if you have, for instance, a time symmetry, I believe that indicates that energy would be conserved. So locally, right near you, general relativity will conserve energy. However, it is not conserved globally, things far away. For instance, the cosmological redshift of radiation. The microwave background used to be all gamma rays. Now it's all radio waves. But it's that way everywhere in the universe. Where did the energy go? It just disappeared because energy is not conserved in general relativity. Potential energy, which is frequently used in Newtonian gravity, is really just a bookkeeping device. It's useful in general relativity also when things are local. Okay. General relativity is typically written in these things called tensors. They're more complicated. You have scalars, which are regular numbers. You have vectors, which are sets of regular numbers. Let's say velocity is a vector where you have an x speed, a y speed, and a z speed, and you put it together and call it a vector. Well, you can have even something more complicated called tensors, and there's different tensors. There would be xx, xy, xz, tensor, x time. These are all things that would occur in a 4x4 general relativistic tensor. Three big ones occur: the Einstein tensor, which tells how space curves; the metric tensor, which we saw a little bit previously, that really tells you distances and times between two events. And the stress energy tensor is actually very key because it tells you where the energy is, and what the energy is what tells space how to curve. So you have to know where the energy is, where it's flowing, and that tells you the stress energy tensor. And from that you get things like the metric tensor and the Einstein tensor, which tells you how things move and the distances between things. Okay, so in flat space, so general relativity creates curved spaces. In flat space, which is what we're familiar with locally, circles have area pi r squared, spheres have volume 4/3 pi r cubed, but in curved space things don't happen like that. Area can be greater or less than pi r squared, volumes can be greater and less. So I'm running out of time, I'll get to my last slide. So here we have examples of triangles. Let's go to red here. This triangle on this sphere actually has an area less than Euclidean. This is the Euclidean area measured here. On this saddle, it's actually greater than Euclidean, and that's a demonstration that the areas and volumes in general relativity don't have to be the same as in regular Euclidean geometry. And with that, I will let off, and we'll see you next time with more strange stuff.